All right, guys, any questions on the homework before we get started? Just one. Because if we were finding the roots like these here, so this isn't on your note sheet. Because like this first one here, we want to find the real roots for the given value. Yes, I have one. So the cubed root of negative 1,331, we know we'll have one real root because we're taking an odd root of this. And we could plug this in. The third root of negative 1,331 is negative 11, because if we multiply negative 11 by itself 3 times, we get negative 1,331. Now the second one, we're wanting to take the sixth root of negative 258. So since we're taking an even root, there's 3 possible choices, either no real roots, 1 real root, or 2 real roots. And because the number inside is negative, we can't take an even root of a negative number. It just does not work and get real roots. The last one we have up here is the fourth root of 2401. And again, even root. So it's either going to be none, 1, or 2. Because it's a positive number, we do have 2 real roots. So we add the plus or minus and take the fourth root of 2401, which is 7, because we could have positive or negative 7. Now the first thing we're looking at today are these here, these properties of rational exponents. And the first one is that a to the m over n power, well, we could rewrite it as a to the 1 over n to the m. Because powers of powers multiply, so we can also split them back apart. Because 1 over n times m is m over n. So that's all we're doing here, is splitting that exponent apart. A to the 1 over n is the same as the nth root of a to the nth power. And the reason we can do this, or would want to do this, is so that we can simplify that radical. We can simplify what's inside and then put it to that nth power. The other property is if that rational exponent is negative. A to the negative m over n. Well, whenever an exponent's negative, we can move it from the top of the fraction to the bottom. And then we just do the exact same thing. Over nth root of a to the m. So when we look at these here, 16 to the 3 halves. What this is telling us, and using this property, we can say that this is the same as 16 to the 1 half to the third. We're just using, again, that our a to the m over n is the same as a to the 1 over n to the m is the same as our nth root of a to the m. So the next thing this is going to tell us is we can rewrite this as a radical. Now the number that goes in that v, that index, would be 2. Well, that's understood to be the square root. Now the question is, what is the square root of 16? What times itself is 16? Would be 4. So doing this gave us a radical that we could actually do. We can take the square root of 16. We know how to take the square root of 16. Now we just have to multiply 4 by itself 3 times, which is indeed 64. Which is telling us 16 to the 3 halves is 64. And the calculator, 16 to the 3 halves is indeed 64. We are able to do it with the calculator, but it also gives us a way to solve this by hand without a calculator. Questions on A before we look at B? Yes, but not everyone will be calculator, because there are going to be some we have to actually do by hand. Because not everyone's going to simplify nicely. And putting it, or rounding, giving the decimal and rounding is not going to be the answer we want. We want it in radical form. So this gives us a way to actually understand what we're doing before we start touching those. 32 to the negative 3/5. A to the negative m over n is the same as 1 over a to the m over n. So we could rewrite this as 1 over 32 to the negative 3/5. And our property then says that we can rewrite this as a to the 1 over n to the m, bless you. So this is the same as 1 over 32 to the 1/5 to the third, and that shouldn't be negative. Yes. And again, from here, we can say this is the same as the nth root of a to the m. So this is the same as 1 over the 5th root of 32 to the third. Now at this point here, we need to evaluate the 5th root of 32. We're trying, thank you. What number times itself 5 times that's going to give us 32? Well, we know the square root of 16 was 4, so we're looking for probably a smaller number for 32. And it will be 2, because if we break 32 down using factor trees, using prime factorization, well, 32 is 2 and 16. Those two multiply together to give us 32. 16 is going to be 2 and 8. 8 is 2 and 4, and 4 is 2 and 2. So 32 is 2 to the 1, 2, 3, 4, 5. Telling us that the number times itself 5 times, that gives us 32, is indeed 2. Last thing we need to do to simplify is 2 to the third power. Well, 2 to the third power is 8. Telling us that 32 to the negative 3/5 is indeed 1/8. Questions on A or B? Questions on how this works? If we look at the next one, 64 to the 4/3, doing exactly what we just did, we can say that this is also the same as 64 to the 1/3 to the 4th. As a radical, we're saying we're taking the cubed root of 64 to the 4th power. We already seen what times itself 3 times the 64 already. It is 4. 4 cubed is 64. Cubed root of 64 is going to go back to 4. Four to the 4th will be 256, because 4 cubed is 64, so we're just multiplying it by 4. And if we wrote that out, 64 times 4, 4 times 4 is 16. So 6 carry the 1. 6 times 4 is 24. With our 1 carry to be 5, giving us 256. Telling us that 64 to the 4/3 is indeed 256. Last one of these here, 16 to the negative 5/4. So if we do this like previously, we can move that 16 from the top of the fraction to the bottom. And we do that to take that exponent from being negative to positive. Just like before, we can break this up, saying that we have 16 to the 1/4 to the 5th, which is the same as the 4th root of 16 to the 5th. At this point here, we need to find out what times itself 4 times is 16, which is 2. Because if we did the factor tree just like before, factor tree, we're just trying to rewrite it as prime factor, something that can't be reduced any further. And the smallest number that goes into 16 besides 1 is 2. 2 and 8. 8 is also has a factor of 2, 2 and 4 is 2 and 2. And if we group those prime factors together, 2, 1, 2, 3, 4, telling us that 16 is 2 to the 4th. So the 4th root of 2 to the 4th would be 2. Well, that does kind of help us out, because the last step is to take 2 to the 5th power. Well, 2 to the 4th is 16. So we just need to multiply by 2 one more time. Just find out that 2 to the 5th is 32, telling us that 16 to the negative 5/4 is 1 over 32. Questions on this here? All right. Now that brings us to solving nth roots. Now this solving with nth roots is very similar to solving our square or solving by the square root method. Our first step is to get the term to the power by itself. Is going to be our first step. And if we look at this one here, we have 4x to the 5th is equal to 128. So for this problem here, our term to the power is the x to the 5th, x to the 5th. We need to get it by itself. And right now, the term that is with it is 4. So we're going to have to divide both sides by 4, because our 4x to the 5th divided by 4 is x to the 5th. Our 128 divided by 4 is 32. So we got the first step done. We got the term to a power by itself, and in this case it was x to the 5th. Our second step is to take the nth root of both sides. We have to take the nth root of both sides, and if we take an even root, we do need that plus or minus. So for this here, the nth root, what is our exponent attached to x? It is 5. So what root would we take of both sides? 5, the 5th root. Because our 5th root of x to the 5th, the 5th root and 5th power would cancel, leaving us with x is equal to. Now we need to figure out what the 5th root of 32 is. It is going to be 2, and with these here, I will let you use the calculator on these, telling us that it is 2. Now our last step, we'll go on and write this here, is to solve. If x is not by itself, we need to get it by itself. We need to solve. X is already by itself, so x is 2. Now there are 4 other solutions, but here it's just asking us to find the real solutions. The number of solutions for any polynomial is equal to the number or the degree of the polynomial. So here the degree is 5, so there are 5 solutions. However, one of them is real, the other 4 are imaginary, they're complex. It only asks to find the real solutions. X equals 2 is the only real solution. The other 4 are complex, imaginary solutions. Questions on this here? All right. Our next one, we want to find the real solutions for x minus 3 to the 4th equals 21. Again, the first step is to get the term to the power, term to a power by itself. Well, the term to the power is what? The x minus 3. Is it by itself? So when we see if it's by itself, so this here is our term, is there anything being added or subtracted to it? No. Is there anything being multiplied by this term? No. So our term, even though it is x minus 3 to the 4th, the whole term is that x minus 3 to the 4th power. So this here would be by itself. The only way it wouldn't be by itself is if we had, say, 4 times x minus 3. Or we had 7 plus this here. We have something outside of the radical. But this here, the x minus 3 to the 4th power is by itself. So we can go straight to step 2, which is to take the nth root of both sides. And the nth root in this case would be the 4th root because the exponent is 4. And the reason we do this is because the 4th root of this 4th power will simplify, leaving us with x minus 3 is equal to 4th root of 21. There is no 4th root of 21. Because if we look at the 4th root, all right, let's clear that all out and try again. 4th root of 21 is decimal. Because we're saying what times itself 4 times? It is 21. Well, 2 to the 4th power is 16. 3 to the 4th power is 81. 21's in between there. There's not going to be a number. There's not going to be a nice number. Normally, that's going to be between those two. Because we could look at, say, 2.5 to the 4th. Not what we have. So in this case here, we'll leave it as the 4th root of 21. But we took an even root, yes? Anytime we apply an even root to both sides, we have to add the plus or minus. This only goes with even roots. Whenever we take the even root to both sides, we have to put the plus or minus. And then lastly, we need to solve for x. Because x is not by itself, we're going to add 3 to both sides, showing us x is equal to 3 plus or minus the 4th root of 21. We always put that number we add or subtract on both sides in front of that plus or minus. And this here, x is by itself. We have solved it. This is done. So for us here, x is equal to 3 plus or minus the 4th root of 21. We could rewrite it as its 2 expressions because really this is 2 separate statements. That x is equal to 3 plus the 4th root of 21 and x is equal to 3 minus 4th root of 21. We could write it out as these two here. Or we can just leave it as that single expression. And that is the worst error I've drawn in a while. Question on this here? Questions on any of this here? If it is simplifiable, we need to simplify it. Let's look at the next one. Find the real solutions of 5x cubed equals 320. Is the term to the power by itself? for this here? No, it's being multiplied by 5. So the first thing we need to do is get that term, that x to the third by itself. And we can do that by dividing both sides by 5. Because 5x to the third divided by 5 will give us x to the third. 320 divided by 5 is 64. Now that we've got that term to a power by itself, we can take the nth root of both sides. And the nth root of both sides in this case is going to be 3. Because the cubed root of x to the third, those will cancel, giving us x. Cubed root of 64 is 4. Now because we took an odd root, we don't put the plus or minus. There's only one real root. And for us here it is 4. Now we haven't done this up to this point. If we wanted to, we could check and see if 5 times 4 to the third is indeed 320. 5 times 4 to the third power is indeed 320. This is true. That is our only solution. Questions on this here? Our next one, x plus 3 to the fourth is equal to 24. I'm going to change it just a little bit. Let's stick a 3 in front. 3 times x plus 3 to the fourth power. I did this. I mean, I can show you and I can say what the answer is if you already solved it. But is that term to a power by itself? No. So what we would do is divide both sides by 3. Because here the 3 and 3 would cancel, telling us that x plus 3 to the fourth power is equal to 8. And just like before, we're going to take the fourth root of both sides. Because the fourth root and 4 will cancel, telling us x plus 3 is equal to. Since we took an even root, we have to put plus or minus. I can check here in a second. Fourth root of 8, not a nice number. Fourth root of 8 is not a nice number. Fourth root of, or third root of 8 is, because 8 to the third is 2. Lastly, to solve for x, we would subtract 3 from both sides, telling us x is equal to negative 3, plus or minus the fourth root of 8. Without the 3, if you'd already solved it, x would have equaled. I must have changed it and didn't change this. I'll have to fix that. Yep, either that or I. Yep, I'll have to change that. Yep. Yeah. I'll have to fix it. Yeah, because that would have been 4 plus or minus the fourth root of 24. Questions on how we did any of these here? Do we feel comfortable with these here? Okay. Let's look at 15 before we call it good. Because 15 is a little bit, not different, But again, that x plus 5 to the fourth power is by itself. So the first thing we can do is take the fourth root of both sides. So here the fourth root and fourth power would cancel, telling us that x plus 5 is equal to, plus or minus, since we took an even root of a positive number, we add the plus or minus. And the fourth root of 16 is 2. Because 2 to the fourth power is indeed 16. So the fourth root of 16 is indeed 2. Then at this point here, we need to solve for the value of x. We would subtract 5. I guess x is equal to negative 5 plus or minus 2. So the question is, and the question, once we get to this point, is can we do negative 5 plus 2? Well, yes. If we can simplify it and not turning it into a decimal and not turn it into a decimal, we need to simplify it. So our negative 5 plus 2 would indeed be negative 3. And our negative 5 minus 2 would be negative 7. We do get two solutions. Questions on this here? And that is it.